All right, in this podcast we're talking about phase transitions or heating or cooling curves. We just want to be really clear about what's happening during phase transitions and how it's different from a chemical reaction. Okay, so if you were to take a substance, let's say this is not quite water, right? Because it looks like a plateau here at 0, another one at 50. Okay, but if you took a substance and made a heating curve by taking it when it's a solid and heating it up and watching what happens until it goes through all 3 phases, and then you did the same thing starting with the vapor, cooling it until it became solid, you would see the mirror image. The heating curve and the cooling curve are the mirror image, right? And if you look right here, this is where melting is occurring, and the analogous spot here would be where freezing is occurring. This is where vaporization is occurring, and this would be where condensation is occurring. Okay, I want to make sure we have those points right. So when we talk about phase transitions, we are overcoming intermolecular attractions, or IMFs, and not breaking bonds. Okay, so we want to talk about, especially in FRQs, about intermolecular attractions. So if you're thinking about, you see a solid starting off down here, nice, neat lattice work, right? When you get to a liquid, all it's done really is come apart a little bit. It's lost some of its organization, still pretty close together. And when you have your gas, you have all these particles flying around, right? Too hard to draw the whooshes. But you're talking about breaking the intermolecular forces. You're talking about going from a solid to a liquid, which causes this nice, neat arrangement to break up. And when you're talking about a vaporization, you're talking about allowing the particles to fly off. And while we're talking about it, I should have drawn this a little bit differently because, which is going to take more energy typically, a melting or boiling. In fact, it's generally going to take more energy to boil than it will to melt, because here I am just causing these particles to become disordered. And here I'm allowing these particles to completely separate. So a big difference in the what's happening here. Okay. So if I look at fusion, which is considered melting, vaporization, and sublimation. So melting, vaporization, or sublimation, which is going directly from a solid to a gas, they require an input of energy. Energy has to be added to allow these phase changes to occur. Okay? They require the input of energy, and they require overcoming attractive forces between the particles. Okay? We did not say breaking bonds. We don't want to be talking about breaking bonds when we're talking about IMFs. Now, on the other hand, in the cooling curve, freezing, this is freezing, condensation, and deposition, which is the opposite of sublimation, require an energy release. So the energy is being lost to the surroundings when these changes occur. Okay. So we release energy, we release energy as the IMFs form, as the particles come back together and achieve a lower energy or more stable state. Okay. Let's just talk a little semantics first. Vapor versus the gas, they are different. So if we're talking about something like oxygen at room temperature, we're talking about oxygen gas. So a gas is a gas at room temperature. Okay, so we're talking about nitrogen or oxygen or hydrogen. It's a gas when we're talking about it. But if we talk about something that is in the gaseous state, that is not normally a gas at room temperature, we call it a vapor. So water, for instance, is normally a liquid at room temperature, but if we have vapor at room temperature, we're going to call it water vapor as opposed to water gas. Okay? So we talk about carbon dioxide vapor. Okay? Okay, so make sure in your FRQs that you are very clear that the changes in phases is due to altering the IMFs, not changing chemical bonds. And the strength of the intermolecular attractions between molecules, and therefore the amount of energy required to overcome them, depends on the molecular properties. So something that has very high intermolecular attraction is going to, that's very, very polar or has hydrogen bonds, is going to take a lot more energy. It's going to have a higher heat capacity to cause that those changes to occur. Okay, so the more polar a molecule is, the more polar a molecule is, the stronger the attractive forces. So polar molecules require more energy to overcome the IMFs in an endothermic phase transition, which would be all the things you see on a heating curve. Okay? And they will release more energy in the cooling curve on anything that's exothermic. So phase changes involved breaking IMFs, not breaking bonds. Okay? Alright, so let's take a look at what's actually happening along the heating curve. We can investigate the changes. So we start with a solid down here, and we heat it at some constant rate, put it on a hot plate, let's say, it begins to melt. So first we have the solid that is being heated. It's being warmed and the temperature is rising until it reaches its melting temperature, and then it hits a plateau. And during this plateau, the temperature is not changing. This is where the melting is occurring. So on the plateaus, you have the phase changes occurring, and all the energy is being used to break the IMFs. Once I have pure water here, or pure liquid here now, I heat it up, I warm it up until it reaches its boiling temperature. Once it's reached its boiling temperature, it stays on a plateau until all of the liquid has been converted into gas. All the energy here is being used to break the intermolecular attractions between the molecules. And then I have a gas, and the gas gets heated. Okay. So let's answer these questions. So do these changes involve physical or chemical changes? Well, they are not breaking chemical bonds, so it's physical, right? They are breaking IMFs. What type of force is involved? Intermolecular forces. Define temperature. Temperature here is defined as the average kinetic energy of the molecules. That's what temperature represents. What conversions involve temperature change? Well, the conversions here, warming, the warming and the cooling, right? So temperature change is only when I'm heating something up, or if I have a cooling curve, you know, the spots where I'm cooling. Okay. Okay, so what mathematical formula is appropriate for calculating the energy change in the process defined in force? So that would be, let's say, warming. So here I have some temperature change going on. I have some heat capacity that is specific to the material, so I'm going to use my Q equals MC change in T. So which conversions involve potential energy changes? The potential energy changes occur at the plateaus, right here on the plateaus, both on the heating and on the cooling. Let me just get my pen back. Okay, so these are at the plateaus, which is all the phase changes: melt, freeze, boil, condense, sublimation, all of them. That's where potential energy is being changed. Kinetic energy is being changed when temperature changes. There's no temperature change here, so these are just potential energy changes caused to disrupting intermolecular forces. So which mathematical formula is appropriate for calculating the energy associated with the process you identified in question 4? Well, question 4 was talking about the warming and the cooling, so it's going to be this equation. How do you calculate Q for the process identified in number 6? Number 6 was where we had plateaus. There is no temperature change here, so if we use Q equals MC change in T, my change in T will be 0, and it'll tell me it will take no energy. But in fact, there is an energy change. So Q here is going to be some quantity times some constant. So the quantity can either be mass or moles, depending on what my constant is. And in the case of phase changes, we're either looking at the heat of fusion, which happens at melting or freezing, or heat of vaporization, which happens at boiling or condensing. So you got to watch for what value you're given here to know whether or not you should use mass or moles. So which portion of the graph represents equilibrium conditions? Well, equilibrium happens when you have a phase change. Okay? When you have a phase at all of the plateaus, all of the phase changes, and that's because the temperature is constant. So kinetic energy is not changing, only potential energy is changing. Okay? So let's take a look at this specific heat capacity problem for a heating curve. It says how much energy is released when 1 mole of water at 20 degrees C is frozen and then cooled to a temperature of -2. Alright, so here we have cooling going on. So I really find it helpful to draw a cooling curve. So I just draw the general shape. So this is water, this is a 0, this is 100. And I'm starting at 20, so this is where I start. I got to get down to 0, where my freezing begins, and then down to -2, where I'm done. So in order to figure out the total energy that's released, I need to calculate the energy at 3 different areas. Q1 is going to be what happens here. Q2 is going to be what happens at the plateau, and Q3 is what's going to happen after I'm done freezing and I am now cooling the solid, so that's going to be Q3. And I'm going to have to add them all together to get the total Q. Alright, so let's take a look at what that involves. Alright, so Q1 is, there's a temperature change down here at Q1, so I need to use the formula that has the temperature change. M times C times change in T. So I look over here at specific heats. This is for water, so it's based on 4.18 joules per gram degrees C, so I'm going to use grams in my quantity. So that's going to be, let me see, I have 18 grams because it's 1 mole. Heat capacity is 4.18 joules per gram degrees. It has it by K, but by C is the same thing. And change in temperature goes, now I'm not looking at the entire temperature change from 20 down to 2. Remember, I'm only looking, let me change my pen color. I'm only considering, where's my pen? This change right here. So it's where it goes from 20 down to 0. Alright, so my temperature change there is 20 degrees C, and this is going to give me 1505 joules. My Q2 is at the plateau. I have no temperature change, so I need to use some quantity times, in this case it's going to be the heat of fusion. Fusion happens down here. Okay, so here I have the molar heat of fusion, so it's per mole. So I'm going to use 1 mole times the heat of fusion, which is 6.02 kilojoules per mole. Now recognize I got kilojoules here and I got joules here, and when I add them together they're going to have to be the same. So this is 6.02 kilojoules, so I'm going to go ahead and change this to joules. That'll be 6020 joules. Alright, then I have Q3, and let me just change that color. I'll make it green. Here I'm talking about this little area here where I go from 0 down to -2. Okay? So I'm changing temperature, so I want, again, MC, changing T. My mass is 18.0 grams. Now look here. Specific heat of ice is different than the specific heat of water. And that's true for a lot of substances. The specific heat is going to vary depending on whether you're talking about a solid or a liquid. So I have to use this 2.05 joules per gram. I'm going to use degrees C. And my change in temperature down here is just this 0 to 2, so it's 2 degrees C. And I have joules here, so what I'm going to... I'm going to get joules in my answer, so this will be 738 joules. So my Q total is going to be Q1 plus Q2 plus Q3. So it'll be 1505 joules plus 6020 joules plus 738 joules, which will give me a total of, calculator says, 7600 joules, and I will change that for convenience to 7.6 kilojoules. Alright, we're going to stop there.